Let us look at the serial port of the ARM processor, that is UART. LPC2148 has two serial ports, UART0 and UART1, which has a single interrupt connected to vector interrupt controller, but the sources of interrupts can be multiple. It has various special function registers like interrupt enable, interrupt identification, FIFO control, line status, scratch pad, and baud rate divisor, LSB and MSB, receiver buffer, transmitter hold register. So these are various special function registers which are associated with the transmitter and receiver of the serial port. Since using the serial port, that is, if you want to connect to the microcontroller's serial port TXT RXT pin to the computer serial port, you require a DC to DC converter like MAX232, which will convert TTL signals into RS232 form. The control registers which are meant for UART is, one is line control register. Line control register, which is a which will decide the format of the data which need to be transmitted, like word length, whether it's a 7-bit, 8-bit data to be transmitted, how many stop bits, parity bit, and divisor latch access bit. So these are various programmable bits to configure the transmitted data. The baud rate, that is the rate of communication, bits per second, is decided by this divisor value. So the peripheral clock divided by this divisor is a formula is given here, is the baud rate. Say for example, if 9600 is the baud rate and the peripheral clock is operating on 30 megahertz, then the value turns out to be C2 in hexa value, which need to be loaded in the LSB portion of the divisor. So this will decide the baud rate. So whenever DLAB bit is set, then the contents of LSB and MSB will be loaded into the divisor. Once the value is loaded, then DLAB bit should be disabled. Similarly, while receiving the data, there is a line status register which will indicate the status of the received data, like whether the data is ready, or while receiving the data, any overrun error, parity error, framing error, and so on. Or while transmitting, the data register is empty or not, transmitter is empty or not, or any error in the FIFO. So it will indicate the status of a receiver or transmitter. There is a buffer, 16 bytes buffer in the UART receiver. This will hold the data, received data. So by using some interrupt or various interrupt sources, one can read the data from the buffer. Similarly, while transmitting, transmitter hold register will hold the data to be transmitted. So again, a 16 bytes buffer is there where the transmitter shift register will shift the contents of the data. So the depth is again 16 bytes. So transmitter has 16 bytes and receiver has 16 bytes of buffer. UART1 is a modem. Along with the transmitter and receiver signal, it also has various modem control signals like request to send, clear to send, data set ready, data terminal ready. So these are various modem controlled signals which are available in the modem control register and status register. So UART1 can be used for interfacing the modems. So the signals are as mentioned, request to send, clear to send are available for UART1. Let us see the board details. On board, you have port 0.0 and 0.1 where TXT and RXT pins are there in LPC2148, and second UART is available on port 0.8 and 0.9, that is pin number 33 and 34. Both of them are connected TXT0, RXT0 and TXT1 and RXT1 to MAX3243 IC, which will convert the TTL signals into RS232 form. COM1 signals are available on 9-pin D-type connector. COM2 signals are available on 3-pin connector. COM1 currently we are using to program the microcontroller by using in-system programming, but at the same time, after programming, you can also use it for data transfer. COM2 is free, but however, you can use it for interfacing Bluetooth or Zigbee modules. In the program example, you should look for 6th example, serial UART test. So in this program, first one has to initialize the serial port, UART initialization. So there is a C program, serial.c. So UART initialization, UART0 initialization means first one has to select a pin selection or with 05 so that the instead of GPIO, the pins are act as a peripherals, that is UART, RXT0 and TXT0. Then in line control register, UART0 line control register, if you load 83, then it will initialize 8-bit data, no parity bit, 1 stop bit, and latch bit will be enabled. Then you can program the calculated value of the baud rate into DLL register, which is LSB of the baud rate register, which will initialize for a baud rate of 9600. Then again disable the DLAB register, DLL register, so that contents won't be modified. So the baud rate will be latched. So this is the initialization. If you look at the significance of these control registers like LCR and DLL in the data sheet, as you can see, the UART line control register, the line control register is meant for programming the transmitter, like how many stop bits, parity bit, and break control bits, and you can also enable or disable divisor latch access bit, so that the baud rate will be updated based on whenever this bit is set. This line status register will indicate the status of the received data, whether the received data is ready to read in the buffer or any overwritten happened because of the overrun error, parity bit is set because of the parity error. So our frame is not correctly received, some bit is lost, so that indicate the framing error. But most importantly, we look for this 5th bit, that is the transmitting holding register empty. So if this bit is set, that means there is no data. Otherwise, if this bit is 0, that means it contains a valid data. So that is how we can, while transmitting the data, whether it is empty or not, we'll have to verify so that we can write the next character without overwriting on the previous data. The baud rate is decided by two registers. One is DLL, other is DLM. DLL is LSB is stored and DLM MSB is stored, which will decide the baud rate of the UART. In the program, once the initialization of the serial port is done, then we are calling a function to write the string to the UART by using put string of the UART0. This serial.c has various functions like send character and initialization of the UART0, UART1, put character, put string, and so on. So the put string uses put character function. What you can see is that this line status register, it is continuously verifying whether the value, that is holding register, is empty or not. So if it is empty, that means it is ready to write to the new character, send character into the T0, U0, THR register, so that the data will be shifted out. So this is how it is continuously verifying the readiness of the transmitter holding register empty whenever you want to write a new character. So that is how the whole string will be transmitted depending on the length of the string. So then there is a slight delay and in the while loop. So let us compile the program and simulate the program. Now as you can see, now this time we want to see the UART0 peripheral, and then if you execute the program, you can see a serial window where the string is continuously transmitted. See in the simulation. And you can also see in the peripheral view, the flags are set about the transmitter holding register and the transmitter empty register. Okay. Now let us load the program into the flash memory, that is sixth example UART test.hexa file. Close the jumper, ISP jumper on the board, press the reset button and start. As you can see, the flash is erased and programming is done. In this example, the serial port is continuously transmitting hello world message through serial port. Since the same serial port is also connected to the computer, we can read the data from the serial port and display it on the computer. So you can go to tools. There is a tool called terminal. You can select the COM1 of the computer. Baud rate, select the same baud rate what you have done, 9600. And then if you say OK, now you remove the ISP jumper, press the reset button. You will notice that on the output terminal, hello world is continuously transmitting. And if you again close the jumper and press the reset button, and it will stop transmitting the text. So this is how a UART is functioning to transmit the data through serial port. Similarly, you can also use get character function to receive the data from the serial port, and then the controller can compare what data is coming from the computer. So there is a get key function is there available, which will verify whether the receiver buffer is empty or not to receive the data. The next example is real-time clock RTC, which is inbuilt feature of LPC2148. LPC2148 has calendar IC, which is 20. It can calculate up to seconds, minutes, hours, years up to 2099. It works based on peripheral clock PCLK. It also has alarm register that can be used to trigger a particular date time, so that on a specific time count it can generate a alarm. It has various registers to hold the data of seconds, minutes, hours, day of month, year, and so on. And based on the increment of these values, it can generate a interrupt. So one can enable the interrupts, or one can enable the alarm based on the value, change in value. So once the match occurs, it will generate a interrupt. The operating frequency of the RTC is 32.767 kilohertz. So you need to derive this frequency by using peripheral clock. So if the peripheral clock is, let us say, 30 megahertz, then peripheral clock divided by this prescaler value should generate the 32.767 kilohertz frequency for the RTC. So there are two resistors, that is pre-integer and pre-fraction. These are the two registers has to be calculated so that 32.767 kilohertz can be generated. So the formula is given here to calculate the pre-integer and pre-fractional values. So if your peripheral clock is 30 megahertz, then since the desired value is 32.767 kilohertz, so the integer is 914 and the fraction is 17280 should be loaded into these two registers. So while reading the data, the RTC has a consolidated registers, so that the register 0 can give you seconds, minutes, hours, week. Consolidated register 1 can give month, year, and 2 register can give you calendar year, and so on. So there are two ways to generate the interrupts by using RTC. In method 1, any time counter register, whenever it increments, like seconds, like in every second you can generate an interrupt. Or in method 2, matching the alarm register. So you can unmask the timer counter register, and then when the match occurs, then it will generate an interrupt. Let us see how to write a program. So the programming example is example number 7, RTC. In this example, apart from initialization of the LCD, we have called one function called RTC initialization. In RTC initialization, first the peak on P in register, that is the power control of the RTC, if you refer page number 37, power control for peripheral resistors. So this resistor will switch off the clock of various peripherals, so that it will save the power. So in our case, PC RTC, if this bit has to be set, so that clock control bit will be set, so that the RTC will get the clock. Otherwise, if it is 0, then the peripheral is disabled to conserve the power. So that is the reason why we have ORed with 0x200 to enable the clock source. Then there is a CCR register to reset the clock. So if you refer the data sheet, page 278, so in CCR register, so setting this bit will reset the RTC clock. So CTC bit is reset. Then clear the interrupt location register ILR, which is given in page 277. So interrupt location register, reading this location indicates the source of interrupt, but initially we want to clear this register, which is a 2-bit register. So counter increment interrupt we want to clear. Otherwise, if you want to clear the alarm register interrupt, then you can clear this alarm register. So this will indicate the source of interrupt. So in the beginning of the program, we have cleared the source of interrupt. Then CIIR, enable seconds increment interrupt. So we want to generate a interrupt on every second, which is given in page 278. So counter increment interrupt register, where one can select the interrupt based on seconds, minutes, hours, or day of month, day of week, day of year, and so on. So in our case, we want to set the first bit, that is generate a interrupt on every second. So that is the reason the value is 0, 1. So after that, how to read the consolidated registers where the data is there. So as you can see, the other registers like alarm mask register, where you can enable or disable the alarm registers. In consolidated time registers, as you can see, they consist of like timer register 0 consists of seconds, minutes, hours, and day of week. Register 1 consists of day of month, year. Register 2 consists of day of year. So the timer counter registers, the name is specified here, SEC, minute, hour, date of month. So you can access these memory location contents by using these names in the program. So that is the reason why we have used these names. And then as discussed, that we have to calculate the integer and fractional value to generate the clock of 32.767 kilohertz. So this is the initialization program of the RTC. So once the initialization is done, then in the main program, again in CCR register, we have set 1 so that the clock control register, in the clock control register, RTC will start. Then in the loop, we are reading the values from the consolidated register of hours, minutes, and seconds, and we are displaying on the LCD. So you can compile the program and you can debug the program. Now you can view the real-time clock of the ARM processor and you can run the program. Now you will notice after 1 second exactly, the contents of the seconds updated, and in the increment interrupt, the as you can see, the interrupt flag will be set, and in the clock tick counter, it will be continuously incrementing. So whenever it reaches the maximum count, the seconds counter will be incremented by 2, and so on. So this is how you can simulate the RTC. So once the simulation is done, similarly you can load the program. The program example is on 7, example 7 RTC. You can close the ISP jumper, press the reset button, and then you can press the start. So the program, first it will erase and will program the flash memory. Once the programming is done, remove the jumper, press the reset button. You will notice the seconds, minutes, hours contents are displayed on the LCD. Examples, slow, or like if you see serial ADC, that means read the data from A to D converter and write the data to the serial port. It's a combination of the previous examples. So if you see, if you load the program, and go to tools, view the terminal, so that you can monitor the contents of ADC on computer screen. Remove the jumper, press the reset button. You will notice ADC data is displayed on computer monitor. So this is how you can transfer the data from the microcontroller, which is ADC value, to the computer's serial terminal. So like that you can practice other projects, sort of mini projects, which is example 9 is a how to interface a SD card and implementation of a file allocation table and creating a file, writing the data into the file is ninth example. In short, it is a FAT. Example 10 is to how to implement a FFT and send the data through serial port. Example 11 is how to use a GPS modem interface to the ARM processor. Example 12 is how to interface a GSM modem to the LPC2148 and so on. So these are the various mini projects one can implement. In this session, we will see how to implement a real-time operating system on ARM platform. Operating system is a abstraction layer between the hardware and the software. Operating system allows to create the application program in a multitasking environment where the task will be executed based on the deadlines. Various applications has various deadlines. So task management is different for different applications. There are various scheduling algorithms are available. So in short, the services provided by operating system are: one is the task management, which is the heart of the system. Then the creation of the tasks and communication between the tasks and its synchronization. And whatever is the resources are available, like memory is one of the important resources. So dynamic memory allocation, then device IOS supervision, and make using of the timers for meeting the deadlines. So these are the various services provided by the operating system or the kernel. So the RTOS basic functions are creating a multitasking environment and scheduling the tasks as per their priorities or the deadlines. So every task has a following fields, what is called task control block. One is every task control block has a identification number, its priority for execution, and its current status, whether it is ready to run in wait state and so on, and the registers which are used by the task, and contents of the program counter and contents of the stack pointer. So these are the at least 6 fields which need to be specified in every task or are the duties of the task control block. So the RTOS will look at the task control block and its priorities and its status. Accordingly, it will schedule for execution. So at any given point of time, the tasks are out of these 5 states. Either task may be currently running on the CPU, or task is ready but not running because another one is currently using the CPU, or task is blocked because waiting for some input output signals or resource to be released, so it is in the blocked state. Created but not executing is the dormant state. Terminated is because it has completed, so no longer active. So at any point of time, tasks are in these 5 states. So let us see how this kind of scheduler we can implement. There are various compilers available for implementation of the real-time operating system. ECOS, MuCOS, RT Linux, RTA, and so on. Like in Windows, we have VxWorks. We are talking about FreeRTOS, which is freely available, no royalties involved. And FreeRTOS is used for various target devices like ARM or MSP430 and so on. So this freertos.org, where the complete manual and the source codes are provided in this on this website. So online reference and examples are available. So the FreeRTOS allows you to create a scheduling the tasks, and it is a preemptive type of scheduler. It has the services like queues, semaphore, communication between the tasks and synchronization, mutex for resource sharing, thread safe encapsulation for C, C++ compilers, and timer tasks and CPU time tracking and so on. Basically, FreeRTOS is nothing but a set of few files of .c and .h files. You can combine FreeRTOS.c and .h files with your own C and header files and compile them together and create one single .hexa file. So once if you compile this, then that header file will take care of your flash memory as well as the static RAMs. Generally, we don't need to modify the RTOS files, free RTOS files provided by the FreeRTOS website. We only merge them or make use of them as a part of our project file. There are two types of FreeRTOS files are available. One is called platform independent, other is platform specific. Platform independent files remain same irrespective of which compiler you are using, but platform specific files are different for different compilers. If you have ready to use platform specific files in the FreeRTOS bundle, these are referred as a ports. Means you don't need to modify them. Ports are not IO ports what we use in microcontrollers. These are ready to use platform specific files. If you doesn't have ready to use port files, then you will have to find out the one which are very closer to your application and then slightly modify as per your application, but you require a lot of knowledge for that. They are usually either C or inline assembly form. There are some universities who have implemented TCP/IP stack, USB stack, file allocation table for SD cards and all for FreeRTOS, but it is not the part of FreeRTOS operating system. You have to install externally. So FreeRTOS is, as the name says, free for commercial use. The documentation is available on the website. When you download the FreeRTOS, usually the files are looks like this, like configuration file, RTOS file, task file, routine file, queue file, semaphore file, list file, timer file, port file, and so on, heap file for memory, and so on. So these are the usual files which are going to be part of your project file. Let us see how to install the FreeRTOS. In your folder, there is a exe file called FreeRTOS v7.4.2. If you double click this file, it will unzip and will create extract one folder called FreeRTOS. In this, if you see this, the files are FreeRTOS, FreeRTOS Plus, and so on. So our files are there in FreeRTOS. So these are the various files which will be useful in the project file. So the procedure for installation is given in ysr procedure.txt file. Once you extract the file, then it will create the FreeRTOS header file. Then first you go to your KEIL compiler, create a project. Let us see how to install FreeRTOS in KEIL environment and write various programs for ARM-7 LPC2148. The same FreeRTOS can be also used for other target devices. So once you unzip this FreeRTOS v7.4.2, which is downloaded from the FreeRTOS website, after extracting the file, it will create these folders. So you will notice in FreeRTOS folder, so these are the various subfolders which will be used in the programs. So the procedure is as follows. First, create a project in KEIL. As you know, go to project and create a new project. Once you create the new project, then as we have discussed earlier also, every project requires one startup file which will initialize the ARM processor. So the startup file is provided in your folders. That is, if you see in the LNT folder, in every folder, project folder, there is a startup file is there. So this is the startup file which you should add in your every project file, so that in this startup file it takes care of the hardware initialization of the LPC2148, like memory, stack, interrupt vector controller, PLL, and so on. So once you create the project, second step is there are couple of files which you need to add as a part of your project file, which are provided by the FreeRTOS software. So from the extracted folder, as you can see, the in FreeRTOS you found the license in source. So in the source folder you will find the required file like task.c, list.c, queue.c, which are available here, task.c, list.c, and queue.c. You add these files, task.c, port.c, list.c, as a part of your project file from this folder. Then the third point is, in the same folder, source folder, there is a folder called portable. In the portable, you will find RVDS. In RVDS, we are right now, our target device is LPC21 series. So in this folder, you will find port.c and port asm.s. So these are the two files as specified in the readme file. You add them to your project file, these two files. So once that step is done, then the fourth step is you need to add the memory management, which is again, you can go to the folder in portable, you will find memory management folder. In this folder, the heap files are there. So you can select heap2 underscore .c and add to your project file. So this is how, in short, in every project, at least the FreeRTOS related source files related to queue, task, port, heap, list, these are the files you will have to add. Once these are part of your project file, then you can write your own main program. So once the required files are added, now you will have to set the path for the KEIL compiler, so that when you compile the programs, the KEIL compiler looks for these files from where it should include. So for that purpose, first you can go to the project, and in project, as you can go for options, say OK. Again go to project, say options for target. Now this time, as usual, device has LPC2148, target is 12 megahertz is the operating speed, internal ROM. So all these things are as usual. Output, click the create hexa file, select the name of the file, Then in C++, what you'll have to make the changes is, first in preprocessor symbols there is a define. So this is the one which you will have to add, which is given here. So this line you add in your define for preprocessor symbols. Then second step is in include paths. You can select the folder. These are the three paths you will have to add. That is first, second, and third. Third is nothing but one single dot, which is nothing but the current directory. So these are the three paths you'll have to add in the setup compiler include paths. So once you've done that, then you can say OK. So that completes the sixth step. Seventh step is again in the project where options for the target in ASM. Here in include paths, this time add this path which is given again in the readme file. So once this is added, that completes the environment set for the options for the target. Now you can write your own program, main program. So the first example is to blink the LED which is connected on port 0.31. So IO direction is set as an output port. Then a task is being created. So now we are that LED blink program we are doing by operating system. So real-time operating system, which is a preemptive operating system. So task is being created. This is the name of the task. Then the name, and then the stack size. What is the size of the stack you want to configure? Then the priority of the task. You can set the priority. So then we are saying scheduler, start the scheduler, and infinite loop. That's all. That's the main program. Nowhere we are blinking the LED. We have only created that task and start the scheduler. So now about the task, as you can see, the task is same as what is created here. And then in the program, in the task, where we have set some delay, and that delay, and then in the infinite loop we are saying set the bit, clear the bit in between the delay function, but not a normal delay, the delay created by the task delay. Okay, so then you can compile the program. And if you simulate the program, now if you run the program, you will notice the last bit will be set or clear based on the task being scheduled and the task priority. So since there is a delay in the task, that can be modified, the task ticks, so that you will notice the how the task being scheduled. So this is how one can make use of the FreeRTOS as a part of your projects, so that you can create a multitasking environment and you can set the priorities for the tasks, and the task will be scheduled as per the deadlines. Now let us see the next example. The next example in LNT folder is serial port, serial programming. Now in serial programming, this time we are creating two tasks. First task has the highest priority. Second task has the lowest priority. Now this program is about serial port, so serial port is being initialized, UART. Now the first task, send one. As you can see, we are transmitting a string, multitasking, a slight delay. Second task is send to. We are transmitting system as a string, slight delay. So now since we have started the scheduler, first one, multitasking, has the highest priority. This will be scheduled first, then the lowest priority will be scheduled. But since nowhere we have taken care of the common resources, because in this case, for example, task 1 is also using serial port, task 2 is also using the serial port. Then based on the scheduler's priority, both the tasks will share the same resource, that is the serial port. So since nowhere we have mentioned that unless the task 1 is completed, task 2 can claim the resource, nowhere that kind of critical code or atomic code is written here. Nowhere we are talking about synchronization of the tasks or communication between the tasks. The tasks are independent, but then using the common resource. Now, if you compile this program and if you debug the program, you will notice that sometimes first task is getting executed, sometimes second task is getting executed, but both of them are claiming the same resource. So none of the strings are completely displayed. So these are the issues related to the inter-task communication where common resources are used between the tasks. So there is a possibility of conflicts. So how to overcome this issue is, as in the same folder, you can refer the third example, that is serial communication with semaphore. So in theory, as we know, whenever we have this kind of a issue of sharing the common resources or communication between the tasks, one can use the kernel objects like semaphore or the mutex. So in mutex, example is same, two tasks are created. First has the highest priority, second is the lowest priority. But the difference is that in the task you will notice when we are executing the first task, we set the semaphore, and after completion of the task we have released the semaphore. Similarly, in the second task we set the semaphore, we have released the semaphore. Only the difference is in the first task there is a delay after the semaphore. In the second task there is a delay, huge delay before the semaphore. Now second task has the lowest priority, first task has the highest priority. Obviously first task will be executed first. But then when it comes to second task, when second task is being executed, it will claim the resource by using the semaphore. But it is not releasing the semaphore because there is a huge delay before that. So then what happens when the first task comes, because it has the highest priority, but the resource, that is the serial port, is not released by the second task, the first task will be unable to use the resource. So this is what you will notice, that how the highest priority task cannot claim or interfere with the lowest priority task, because the lowest priority task has claimed the resource by using the semaphore. So this is the issue of inter-task communication. So compile the program and when you execute the program, run the program, you will notice first time both the tasks are executed because first has the highest priority, second has the lowest priority. But after that, you will notice that highest priority task unable to execute because the lowest priority task has already claimed the semaphore, claimed source by using semaphore. So now you will see again system is getting displayed not the multitasking, though it is the highest priority. Okay, so let me make a small modification in the program. Instead of having the delay before the semaphore, if I put the delay after the semaphore, now you will notice that first time both the tasks are executed. After that, only first task is completely getting executed, but not the second task, because the first task is getting priority every time. Okay, now let us see the fourth example where we will meet the deadlines of the tasks by using the timers, and we also have the task which have the priorities. So that is soft timers. So in this example, what you can see is there is a timer 1, there is a timer 2, which is a system timer, and we have initialized the deadline 2000 ticks for first one, 4000 ticks for the second one, which is in milliseconds. Then we have created a task like in earlier examples, which has set the priority of 2. Now we have start the scheduler. Now you will see the as usual the send one is the one task which will be scheduled by the scheduler, but this timer 1 and timer 2 are the timer tasks where the deadlines are set, but all of them are using the same resource, that is UART 0, which will transmit the string multitasking in timer 1 in timer 2. A semaphore is being used here by task 1, but the timers are using the deadlines. So as per the scheduling time, these tasks will be scheduled. So this is a multitasking environment where the deadlines are met by using the scheduler timer. Now you will, when you execute the program, and if you run the program, first time the multitasking is executed because that was the task which we have created has the highest priority. Though we have created the 2 more tasks by using timers, but then they have some deadline 2000 ticks and 4000 ticks. So once the time is up, then those tasks will be executed. So after completing the task 1 2 times, now let us see which task will be executed. So now you can notice timer 1 is executed, and then immediately first task is being executed, which is scheduled by the scheduler as per the priority. Now again the first task being executed. Now you will notice this time timer 2 deadline is met, so it has completed immediately. Timer 1 is because every 2000 is the shortest time interval is executed after completion of the timer 2, and then the first task is executed. So you will notice the rate of repetition and the priorities and the deadlines, how they are met. So this is a typical example of a real-time operating system and then preemptive type of scheduler in a multitasking environment. So all these four programs, you can not only simulate them, but you can also download these programs by using FlashMagic software. By using FlashMagic software, all these four programs can be tested. For example, you can close the jumper and reset the reset button, and you can, for example, serial with critical, for example, load this program, start it. So in this case, you will notice that one task will interfere with other task because they are sharing the same resource without using any semaphores or kernel objects. So how to verify in real time by using your target board is, you can go to tools and you can use the terminal to monitor the serial port. You can remove the jumper and press the reset button. Then you will notice that the data being transmitted by using serial port. So the same results you will get, that either first task or second task are completely executed because as per their priorities and deadlines, one is interfering with the other because the resources is the common one. So this is how it's not only simulation the programs, you can also download the programs on target board and verify various kernel operations. Okay.